All right, in the previous class, we started to look at the linear regression, right? Topic that's familiar to you from, hopefully, the USM 231, elementary statistics. And what we did is we looked at the file that contains data on cars, trying to predict the price of the car based on only one variable, right? So let's go ahead and open up the file all over again. So go ahead and launch jump. And in the list of recent files, that's what you should see, right? You probably will see on the top of the list Toyota Corolla, right? Data that you downloaded in the previous class. If you didn't, then go to Scholar. It's posted in jump file. But otherwise, go ahead and open up Toyota Corolla. So, reminder, what we're doing is we're trying to predict the price of the car at the dealer's lot based on only one variable. In the previous class, we discussed that in actuality, the price of the car has a lot of factors, right? Mileage is one of them. Other is probably the make of the car, the brand. Another is how old is the car, how many owners it had, right? Color can be a factor. Engine size can be a factor. Whether or not the car was in an accident definitely is a factor, right? But we said all of these things, as important as they might be, probably they don't come close to the mileage, right? Mileage is probably the single most important factor if I have to pick and choose, right? Which one affects the price the most? That would be mileage. So therefore, what we decided to do is this. We said, let's try and model the price of the vehicle as the linear function of the mileage, odometer reading. So therefore, our model looks like that. Price equals to, we said, beta 0, which we discussed, is going to be our vertical y-intercept, right? Plus the slope, beta 1, multiplied by mileage. That's plus, right? Hold on. That is plus, multiplied by mileage. So that's the equation that I'm going for, okay? All right, and what we did in the previous class, we took the file that contains, by the way, 1,000 cars, right? And prices are in euros, so this is a European data set. Mileages, really, these are kilometers, right? Okay, so, and then here's how we built the model. We said, let's go ahead and click on the fit model. You can also access that through the analyze menu, right? So, fit the model. And price is my variable y, which is target. If I have a target variable, I'm dealing with a supervised learning tool, right? So therefore, regression analysis is a supervised machine learning technique. Okay, and the mileage, I'm going to add mileage into the list of effects. Okay, and then I click the run button, bless you, and here is my output. It has a whole bunch of different parts and pieces, but I'm mostly interested in one of them right now, okay? Which one is that? This one, right here. It says parameter estimate. That's essentially your main output, okay? That contains parts and pieces of the equation. The unknowns in my equation are slope, beta 0, and the intercept, beta 1, right? So that's primarily what I'm looking for, okay? And there right here, in the parameter estimates, it's the estimate of the intercept and the estimate of the mileage. So that's my beta 0 intercept, and that's my slope for the mileage beta 1. So therefore, my model is, let's write that down, price equals to 15,816.8, I believe, minus sign, right? Let's see. All right. Minus sign right there, 0.0631 times the mileage. Okay, so minus 0.0631 times mileage. Okay, that is my model right there. So knowing this model, I can predict any car's price, right? So for example, let's say I have a vehicle with 10,000 miles on it, all right? Then what's the price is going to be? Well, very easy, okay? So in order to predict the price, all I have to do is take 10,000, plug that into the equation, minus 0.0631 times. My mileage, I believe, is just straight mileage right in my file. So multiplied by 10,000, and whatever comes out of that would be the estimate of the price, right? Okay, I can actually do that either using a calculator or something that's called a profiler. Okay, so here it's actually a pretty cool tool built into the jump. So if you go to the red triangle menu, okay, do you see the factor profiling right there? Okay, factor profiling, and go ahead and pick the first option on the menu, profiler, and it adds the graphical tool, really, a profiler, okay? So that's essentially my straight line prediction equation, right? My model. And I can modify the mileage, and over here I will have different values, right, for the response. So, for example, if I'm dealing with 10,000 miles, or kilometers in that case, right, I just change the mileage, and here is the answer. Okay, it's going to be 15,185 euros. That's the expected price of the vehicle. 15,185. Okay. 185. Okay, cool. Well, let's do a couple of things with this model. Okay. Thing number one, the easiest thing to do would be to interpret my coefficients. Okay. What are the coefficients? The slope. That's the intercept, and that's the slope, right? All right, so let's go ahead and discuss the interpretation of the slope first, okay, because it's probably easier that way. What happens if I put more miles on the vehicles? Like I'm taking a car and I'm driving 1 extra mile. What happens with the value of the vehicle? It decreases, right? So let's say that this equation right here gives me the price if the mileage has a certain value, whatever it is, right? I can plug in the mileage, and that gives me the price. What happens if I increase the mileage by 1? So I'm putting an extra mile on the vehicle. In this case, my mileage goes up by 1, right? So mileage becomes mileage plus 1, correct? Putting an extra mile on the vehicle. So therefore my new price of the car is going to be, I'm just going to plug that into the equation, right? 15,816.8 minus 0.0631, whoopsie, 0631, multiplied that by mileage, whatever it was, old mileage, right, plus 1, okay? So now I'm going to do this. I'm going to say, well, let's separate things into this equation, right? So 15,816.8 minus 0.0631 times my old mileage, right? Whatever it was before I put an extra mile in that. Mileage old. But I have this additional 1 times the slope, right? So therefore, over here I have minus 0.0631. Okay? So this part of my equation is what? 15,816 minus 0.0631 times old mileage. That's my old price, right? That was before I put an extra mile on it, right? So therefore, that's my old price right here. Look at that. After I put 1 mile on the car, my new price is take the old price and subtract from that, and what's that value? That's exactly my slope, right? So my interpretation of the slope is like that. Every time when I put an extra mile on the car, okay, everything else remaining the same, right? It's the same vehicle, same age, everything, number of accidents, nothing changed except there is an extra mile on the car, okay? My mileage goes down by, my cost of the vehicle price goes down by 0.0631, okay? So in other words, every mile that I put on the car drops the value of the car by about 6.31 cent, right? Euro cent, that is, okay? Make sense? Because prices are in euros, right? That's 0.063 over euro, right? So 6.3 cents. Michael?
Why are you subtracting the 0.0631 from the old price?
Well, because here is, see that? That's my slope, times this plus 1, that gives me minus.
So if you do that thing, like that will give you the new price then?
Yeah. So the new price is old price minus the slope of my equation, right? So the interpretation of the slope is that's by how much my target variable changes if one of my predictors changes by 1, right? Goes up by 1. Okay? Simple as that. Very straightforward interpretation, okay? And that's, by the way, one of the ways to price the cars, right? You know by how much the value of the car drops with every extra mile. So you take a price of the brand new car, subtract the depreciation in terms of mileages times the value that every mile takes away, and that's your value of the car, right? Right there. Okay, so can we interpret then the slope? So again, here's my equation. Not the slope, I'm sorry, intercept. Price equals to 15,816.8 minus 0.0631 times the mileage. I'm going to abbreviate MIL. Something like that, okay? Well, so what's the interpretation for that number, if there is any? Well, here is what I'm tempted to do. What happens if I set mileage equals to 0? That part of the equation disappears, agree? Slope times 0 gives me 0, therefore the price is equal to just my vertical intercept, right? And what's mileage equal to 0? What's the other way to say that? Mileage equal to 0 means you're dealing with a brand new car, right? So therefore, this number, 15,816.8, I'm tempted to interpret that number as the value of the car if mileage is 0 or it's a brand new car, right? That is a valid interpretation only if mileage equal to 0 is a part of my data set, okay? So let me explain you what I mean by that, okay? And it is actually painful. So here is the plot, all right, of the residuals. I guess before we get into the what's plot of the residuals, let's discuss what is a residual, right? So let's get to the discussion of what the residual is. Remember when we started this whole problem, we said in actuality, if you plot price versus mileage, you're not going to have a straight line, right? You're going to have a lot of points that are all over the place. They look like random cloud, right? But hopefully the mileage goes up, the price goes down. That was our initial logic behind that, right? So that if I feed a straight line into my points, that straight line will capture me the general trend in the data, right? It'll tell me mileage goes up, price goes down, and that in general how it happens, okay? But what will happen is every time when I predict, let's say that this is my mileage that I'm going to pick up, okay, X1. I know that for that specific X1 number of miles, this is the actual price, right? What would be the price that is predicted by my model? It's going to be a point on a straight line, agree? That's what I would predict, but in actuality there is a difference, right? So therefore, every time when I'm using my equation as a prediction formula, I'm making a mistake, right? How large of a mistake? Well, it depends, right? Over here, that was the amount of the mistake, right? So therefore, I can compute the amount of error or my misprediction, right? I made a prediction, but it was off for obvious reason, right? Whatever is the point on the line is not the same as the point in the data. So error is the actual data, AT, A stands for actual, minus, let me erase that, minus FT. FT is my forecasted or predicted value, okay? So errors can be large, can be small. So in this case, it's kind of medium, right? So let me find a large error and positive. So this one right here, okay? Let me erase that point. So let's say that this is my another value of the mileage, X2, okay? That's the actual value of the car right here, okay? That is what I would predict using the equation, right? I underpredict for that specific car, and that's the amount of error, okay? So in this case, the error is positive, right? Because the data A2 is higher than my forecast F2, okay? So if I compute the error over here, error is positive. Okay, over here, in the first one, X1, my actual data is low, my forecast is high, right? So therefore the error is negative, right? Errors can be negative and positive, and what characterizes the good model is negatives, they're approximately the same as positives, right? Number of positive errors that I'm making is about the same as the number of negative errors that I'm making, right? So I'm as frequently over-predicting the price as I'm under-predicting the price, okay? If I'm going to start having more positive errors, like that, okay, that means that I'm more under-predicting the price, right? So therefore, I'm more inclined to lower the price of the vehicle. So therefore, I have a bias in my model, right? It tends to lower the price of the car. That's bad. Other way around is also working, right? If I have more negative errors, just like this one over here, that means my forecast more frequently is above the data, right? Which makes the error negative. So therefore, my model is too optimistic. It tends to over-predict the prices, right? It's biased again. I want reasonable balance, right? I want 50-50, roughly speaking. Half of my errors should be positive, half of my errors should be negative. So if I add them together, they kind of cancel each other, and on average, in a sense, I'm getting 0, right? Make sense? Errors, you, I'm sure, remember from statistics class, in statistics are called residuals, right? So another term for the error is a residual. A residual, okay? All right, so here is my residual plot, okay? So let's kind of discuss what's the residual plot. Here, I'll make it bigger. Residual plot is nothing more than taking, like, let's say this point right here, okay? That is row number 189. Whatever was the value of the mileage, it's right here. So it's approximately a car with approximately 5,000 miles on it, right? Or 5,000 kilometers on it, okay? So this plot essentially gives me a distribution of my errors, right? That's why it's called price residuals. So essentially for every vehicle, where I know the mileage, I do know the mileage for each vehicle, right? I can use my equation. I can get a prediction. I know what's the actual price. I can calculate the difference, the error or residuals, and I can plot the residual on that chart. Okay, so every point on this plot essentially is an error. Okay, by how much my price is off. All right. Now, what does that plot tell me? The reason why I brought it up primarily is to see if my range of values does include values close to 0. Remember, because the whole thing started, I wanted to interpret that number from my equation, the vertical intercept, as the price of the brand new car with 0 mileage on it, right? Well, the only way how I can do that is if I build my regression based on data that actually includes values close to 0. I'll explain why it may be important. Here, okay? I don't know how many of you bought the brand new car, but what's the rule with the brand new car? The moment when you drive the brand new car off the lot, it becomes less valuable because it's a used car now, right? So you paid a dealer $20,000, but once you drove 1 mile, the car is yours. You can sell it for $20,000. It drops in the value immediately, right? It's not brand new anymore, it's used basically. So what can be happening is this one, okay? Suppose, in order to build my equation, I used the mileages between 10,000 and let's say 50,000, okay? So I got a whole bunch of cars with this type of mileage on them, okay? And 10,000 it was high price, and then it started to go down, something like that, okay? And in this case I'm saying, wow, great. You know what? Hold on. Let me make it less slopey, so to speak, okay? Less steep, like that, okay? So this is my equation, all right? So I have an equation which says price is equal to my intercept plus the slope times the mileage. Fine, okay? So this is my equation. And then I'm going to say, well, interpretation of the vertical intercept is set the mileage equal to 0, and that will give you just the vertical intercept, the price of the brand new car, right? Essentially what I'm going to be doing is I'm going to be saying, well, that means that this straight line is still valid if I continue that into the area where I don't have points, right? Still applies, okay? So therefore, here is where the straight line meets the vertical axis. That's my vertical intercept beta 0, and that's the value of the brand new vehicle with no miles on it. Here I'm making an assumption that this equation will still apply in this zone where I don't have data, right? Well, we just discussed. What happens is you drive the car from the lot, it drops the value immediately, right? So it's possible that in actuality, if I do have data, the data behaves like that, right? So you drive the car off the lot, price drops, value drops immediately, and then it kind of flattens out, and then it becomes a straight line. Is that possible? It is possible, right? In which case, my interpretation of that as the brand new car value wouldn't be a valid interpretation, right? This is the brand new car value. Just because the straight line doesn't hold in this white area where I don't have points anymore, okay? So it's a question whether or not you have data. But luckily, do I have data for the low mileage cars in my data set? Looks like I do, right? Look at this one right here. This one is row 187. Oh, hell, I don't want to look at row. Let's take a look at it, okay? Row 187, let's highlight it and let's go back. And it's supposed to be highlighted over here as well, right? So how much was the mileage on this one? Mileage was, oh God, is it 243,000 miles? Is that it? Oh God, something is wrong, right? It's the price predicted. I'm sorry. Yeah, it's the residual plot, not the price versus mileage. Then it would be great. But price versus the predicted value, right? Price versus predicted price. So it's not quite exactly that. Okay. Well, let me take a look at if I have low mileages in my data set. So let's take a look at the distribution of the mileages, just for the heck of it, right? So I'm going to build the distribution of the mileages and see what are the highest, lowest, etc. Okay? So let's go ahead and do the mileage distribution, something that we did like a month ago, right? Okay, so here is the distribution of mileages. Let me stack it. What's my minimal? Minimum is that's maximum, right? 243. The minimum is 1 mile, right? Is that looking like a brand new car to you? Pretty much, right? So therefore, do I have cars in my data set that are low mileages, almost brand new? I do, looks like, right? I do. In fact, if you look at the distribution, that's where the majority of cars are coming from, right? How do we call that type of distribution, by the way? By the shape. Is it symmetrical distribution? It's not symmetrical, right? How do you call the distribution that has a bunch of data at the beginning and then kind of a long tail extending to the right? Skewed. Positively or right skewed distribution, right? Which tells you that the majority of the vehicles that I have in my data set are actually right here, right? They tend to be on the lower end of the mileages, right? And only less and less vehicles, the higher mileage I'm looking at, the less vehicles I have, right? So the majority of my vehicles are either brand new or close to brand new, right? So therefore, I actually have the regression. Let me erase all that stuff, right? I actually have the regression, which apparently is built on the entire range, right? Which includes values close to 0 mileages, right? So therefore, when I say that this slope, 15,816.8, is the value of the brand new car, is that a valid, reasonable interpretation? Yes, it is, right? Because my data set does include low mileages, right, in it. Okay. Any questions? Here's one more important thing, okay? Let me go back to my equation. Look at that. My slope is 0.0631. Does it look low to you? Numerically? It does, right? So, here is what I'm going to do. Let's discuss hypothesis testing, okay? You remember probably hypothesis testing from statistics, right? Very important topic. Okay. Is it possible that this slope I have in my model purely by accident? In other words, is it possible that I selected my 1,000 cars in a lucky way that gives me all this negatively sloped line and everything? just by the randomness of selection. In other words, if I pick another sample, I look at the distribution, it will be horizontal. That's a possibility, right? I could get unlucky sample or lucky sample, or whatever you want to call it, that shows me this trend, right? Because the slope is so small, it's almost horizontal, right? The value of the slope is very little. So, is it possible that I'm getting this equation purely by randomness? Purely, I got sample that gives me the equation. Lucky choice. Could be, right? So therefore, what I need to do actually is to test the hypothesis. Is that a statistically significant model? So here's, ladies and gentlemen, what we're testing. Okay, let me create a new page. Hypothesis. So model significance, right? Model significance. Significance test. Now let's discuss topic which I'm sure you need a refresher on. Okay, hypothesis testing. Remember that in statistics, you probably studied a lot of hypothesis testing, right? Every time when you test hypothesis, there are two of them involved, right? There is a null hypothesis, which we call H0, right? And there is another one which we call what? H1 or A. A stands for alternative, right? So hypothesis testing always involves null and alternative. Null and alternative are mutually exclusive statements, right? In other words, if you write out the null, in order to write the alternative, you just reverse it, and that becomes your alternative, right? So only one of them can be true at any point in time, either null or alternative, right? When we start the hypothesis testing, we believe that the null is true, right? I don't know if you had discussion. Let's kind of discuss that. The connection actually between statistics and where the hypothesis testing kind of similar to the real life is legal proceedings, right? I don't know if you had this discussion or not in statistical class. So in legal proceedings, when somebody is being accused of doing something wrong, right? There are two hypotheses that are being tested. Number one is defendant is innocent. And number two alternative is defendant is guilty, right? You probably heard the phrase innocent until proven guilty, right? Let's show. So that's the premise how the hypothesis is being started testing, right? How the case is being brought to the jury. So jury, when they start hearing the case, they believe that the defendant is innocent until we hear the evidence. Then, based on the evidence, we will decide, is it still true that he is probably innocent, or is it incriminating and heavy, so that we will switch our belief and claim now that the defendant is guilty, right? But the original statement is innocent until proven guilty. So now is true, okay? Same thing happens in statistics, okay? Now is true is how we're going to start testing the hypothesis. And the purpose is to find out, is there enough evidence to support the alternative? If there is not enough evidence, then we're going to stick with null, right? So how does that apply to our situation? Remember our discussion that it seems that our slope is very small, right? Very close to zero, which means that my straight line is very close to being flat. And if the line is flat, that means that no matter what mileage I have on the vehicle, it does not impact the price, right? If the horizontal line, high mile, low mile, doesn't matter, it's still the same price, right? So here's what I'm testing, ladies and gentlemen, okay? My null hypothesis is going to be that this slope, remember slope is beta 1, right, is as good as equal to 0. In other words, this equation that I got with all this slope, negative, whatever it is, right, I got it randomly, by accident of choice, by randomness of choice of the sample, okay? I got sample so lucky that it does show me this trend. But in actuality, there is no dependency, there is no linearity going on here. It's just a flat line, okay? And price is not impacted by the mileage, okay? So therefore, if slope is 0, it means that here's my equation, right? Price equals to vertical intercept plus the slope times the mileage, okay? If the slope is 0, that means that this one is 0, and mileage is not important, right? So therefore, if I find in favor of alternative, it means that the model, I'm going to write it out, model is not statistically significant. In other words, Mileage and price are not correlated with each other at all, right? There is no relationship between them. Model is not significant. Okay? That's what happens if I find it in favor of my null hypothesis. Alternative, I told you before, right? Alternative is opposite of null, okay? If my null says that the slope is 0, the alternative must say what? Not greater, but just simply not 0, right? Can be positive, can be negative, anything, right? Not 0. So therefore slope is not equal to 0. Which means that I cannot take mileage out of the equation, it has to stay, right? It is attached to a slope, non-zero slope, okay? So therefore, I'm going to say here that mileage is a statistically significant variable. Significant variable. I'm going to abbreviate variable, okay? And that's what I'm going to test. All right? Now, here is $1 million question to you guys. How do we test hypothesis? How do we pick between null and alternative? What do we compute? P-value, exactly right. We use the p-value, right? And p-value, what do we do with it? Let's say we have a p-value, 0.0395. How do we say which one is true, null or alternative? How do we pick? We compare it against what?
You have to see if it's like less than 0.05.
0.05 or something, right? So that something 0.05 we call significance level, right? So therefore we have to compare it against alpha, right? That's what Greek letter we used, right? Alpha is significance level. Significance level, okay? All right, so what happens if, okay, let me start a new one, okay? So there are two outcomes, right? If my p-value is less than alpha, what do? There are two options, right? We either keep believing in the null, or we reject the null and start believing in alternative. So if p-value is less than alpha, which one is there? Do we reject the null or do we keep the null? Reject the null, right? If p-value is small, we reject null hypothesis. We reject null in favor, I'm going to write it out in full, in favor of alternative, right? If p-value is small, we reject the null hypothesis and start believing in alternative. Otherwise, if p-value is higher than alpha, then we, statisticians say, fail to reject the null, right? Remember, we start with believing null. It's a question of, do we still believe in it or do we reject it? So if p-value is less than alpha, we reject it. Otherwise, we don't reject it, right? So if p-value is less than alpha, fail to reject null in favor of alternative H1, okay? Two outcomes. Okie dokie. Now let's discuss another thing, okay? Before we kind of look into our specific case, right? What do we have? A significant relationship or maybe a bogus one, which is random, right? Alpha, right? Question that people may ask. What level of alpha to choose? Now, Michael told me that it's 0.05, right? Okay. Statisticians in actuality use 3 different levels of alpha, standardly. I mean, it can be anything really, okay? But standard way how hypothesis testing is done is there are 3 different levels of alpha. It can be 0.1, it can be 0.05, and it can be 0.01, okay? So, let's discuss what are the differences, right? 0.01 is considered to be a weak test, okay? So this is a weak evidence, okay? Weak evidence to support H1, okay? Why is that? If my p-value tends to be relatively high, for example, 0.08, 8%, then I will reject the null. So anything below 10%, I will reject the null, right? So in other words, if the probability to see what I'm seeing is less than 10%, that's when I'm going to reject null in favor of alternative. That's considered to be relatively high probability. Sometimes statisticians say, that's a weak evidence, I want strong evidence. P-value has to be smaller for me to get my results, okay, to reject the null in favor of alternative. In other words, the evidence should be more incriminating, more rigorous test, okay? In this case, they are using 0.05. And 0.05 is actually standard way to test hypothesis. That's why Michael told me 0.05, because unless anything else is specified, it's 0.05. So 0.05 is a standard alpha. Okay? That's most frequently used probably. But if statisticians want even stronger evidence to support their alternative hypothesis, then they use 0.01, 1%. Okay? If your p-value is less than 1%, that is considered to be strong evidence. Okay? Strong evidence to support alternative hypothesis. Okay? So in other words, let's say, for example, my p-value is 0.07, okay? In this case, I would find in favor of alternative only if my alpha is 10%, right? Because then I would reject the null. In other two cases, if it's 0.5 or 0.1, I wouldn't reject the null, right? I would keep the null. So that's why it's not so rigorous test. When my p-value is 0.03, I would reject in favor of alternative if alpha is 10%, right? I would reject if alpha is 5%, but not if it's 1%, right? So therefore, it's considered to be more rigorous test. And if I have really, really small value of alpha, something like 0.001, then I would reject the null if alpha is 10%, if alpha is 5%, if alpha is 1%, always, right? So that's considered to be the strongest evidence that supports the alternative hypothesis, okay? So kind of 3 levels that statisticians are using. Okay, so all of that we have to apply, right? I mean, surely I'm going to test you on that. So if you didn't pay attention, then you're in big, big trouble. That's given, right? But how does that apply to what we just did here in class? Remember, it was a discussion about whether or not my slope is a sign of real relationship that exists between the mileage and the price, or maybe it's a random fluke by the choice of a lucky sample, right? So therefore, here's what I'm testing, okay? Just like what I told you before. I'm going to test 2 hypotheses. Null is that the slope can be replaced with 0, and the model will be just as good as the one that I currently have, okay? Get rid of slope, eliminate mileage out of the equation, and you're going to be stuck with just as good of a model as this one, okay? And the alternative is, no, slope has to stay non-zero. So therefore, this model is statistically significant. There is a relationship, statistically significant relationship between the mileage and the price, okay? So in order to test this hypothesis, I need the p-value, right? Just like what Michael told me. Hypothesis means you have to have a p-value. Where is p-value? Well, let's go back to our analysis. Okay, analysis, the part of the analysis that I'm looking at is right here, parameter estimates, okay? You see that one? Intercept, blah, 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 numerical value, mileage, numerical value, and at the end, there is a probability of greater than absolute value of t. That's a p-value right there, okay? So my p-value is 0.0001, ladies and gents. Okay, so let's go back here. P-value 0.0001. Does it matter against what alpha I compare that? 10%, 5%, 1%, it's still going to be lower, right? So whatever alpha I choose, my p-value is less than alpha. What does that mean in terms of choice between null and alternative? I reject the null, right? I reject the null in favor of alternative. And what does my alternative say about my model? My model is statistically significant, right? Which means that mileage is a statistically significant predictor of the price. That's my conclusion, okay? So this model is not random. The chance that it's random, I picked a lucky sample, is very, very small. This is the chance that my model, in reality, has nothing to do, mileage has nothing to do with the price. It's just, I picked a lucky sample. Very small, slim chance, okay? So therefore, it is a sign that this model has something to do with reality. And mileage is a statistically significant variable, defining the, price, right? Okay, make sense? So that was kind of a brief refresher back into the future, I guess. Well, back into the past in our case, right? Kind of reminding you the material that you learned a couple of years ago, right? Okay, now let's discuss, we still have, I believe, about 5 minutes or so, yep. Let's discuss the goodness of fit, okay? Because my model can be good in predicting the values, the prices of the car, or it can be not so good. How do we judge? Remember when we discussed the classification trees and regression trees, not regression, classification trees, which performance measurement, bless you, which performance measurement did we use to judge if the model is accurate or not so accurate in classification trees? Misclassification rate, right? How often my model is wrong, false positive or false negative. The reason why we used false positive and false negatives are because that's what we're predicting, right? We predict categories, right? It's either 0 or 1. There is nothing in between. If I predict 0.7, I got to say, well, 0.7 is 1, really, right? If I predict 0.3, it's 0, right? So I have to say it's either 0 or 1. So therefore, I either classifying correctly or not. Here, I'm not classifying anything, really, right? I'm predicting a number, okay? When the model predicts a number, the most popular, hands down, measurement is R squared. We discussed R squared before, right? Let's do it again because it's so, oh my God, important, okay? So, in order to judge goodness of fit, how nicely my model follows the data, how closely it follows the data. For the predictive models, just like regression is predictive model, right? I predict the price of the car based on the mileage. We use R squared. R squared, okay? Let me start a new thingy here. Here is the definition of R squared for all times, all countries, everywhere in the world, okay? R squared equals to the percentage of variability. I believe I wrote it out once, right? I'm going to do it again because that's an important part, okay? Percentage of variability in target variable, target, just like retail, right? Target variable, which is explained by and attributed to variability in predictor variables, okay? Variability in predictor variables. Sometimes predictor variables are called regressors, okay? We regress the price based on a bunch of regressors, okay? Regressors, okay? That's a complicated phrase which with very, very obscure meaning, right? What exactly does that mean? Here, let's go back to our model, right? How good of a model is that? Well, first of all, let me ask you this question, an obvious one, I guess. R squared can be between 0 and 1. Let me tell you right off the bat, okay? That's the difference between R squared and the coefficient of correlation. Coefficient of correlation, which we discussed not so long ago, is between -1 and +1, right? R squared is between 0 and 1. If my R squared equals to 0, that means that my model doesn't explain ain't no nothing, okay? So variability in my predictors, which is mileage in this case, right, explains 0% in the price, which means that my model is as good as nothing, really, right? I don't have a model, okay? On the other hand, if R squared is 1, that's as good as it gets, right? Which means that my predictors, whichever I choose as independent variables, they explain 100% everything that's going on with my target variable, okay? Now, realistically speaking, it's never 0, but oh my God, it's never 1. Okay? There are no models that give you perfect 1. So sometimes, not sometimes, but most of the cases, your R squared is going to be somewhere in between 0 and 1. Which one do you think is best, 0 or 1? 1. So the closer your R squared to 1, the better off you are. Simple as that, okay? So let's take a look at our model, right? Okay, so our model, where can I find R squared? Right here, in the summary of fit, okay? R squared in my model is 0.3556. So how do I interpret that number? Here's the interpretation, verbal, okay? I mean, here is the formal interpretation. Percent of the variability in target explained by and predicted by the variability in the predictors, okay? That's obscure. Specific to my problem in hand, I can say that 35.56% of variation in prices from car to car is because each car is different from another car in terms of the mileage, okay? The differences in terms of prices from vehicle to vehicle are because of multiple factors, right? Because of mileage, because of make, year, number of accidents, color of the car, extra features, all these things, beautiful, okay? The variability in mileages from vehicle to vehicle explains about 35.6% of differences from car to car in terms of the vehicle price, okay? So this variable by itself, single-handedly, explains about 35% of variation in car prices, okay? Is it a good model? I'd say it's okay. It's a decent model. The closer to one, the better off we are, right? So one variable explaining 35% of what's going on is PDG. Pretty darn good, actually, okay? So probably we can improve the model, right? There is clearly room for improvement, right? I can make the model better, hopefully. How, by the way? By adding more aspects of the reality, right? Here I said mileage is the only thing that matters. But we know that it's more than a mileage, right? So we're done for today pretty much. On Friday, right, we're going to look at what will happen to your model accuracy or goodness of fit if you start adding more things into the model. And you can guess, right, what we'll see. We'll see R squared going up and up and up, right? Okay. So we're done for today. And we'll finish, hopefully, this topic in the next couple of classes.